I think it's time for starting this session. Let's invite the first speaker.
Hey, good morning, everyone. Thanks for coming. My name is Janice Postal, and I'm going to present our work on sampling-free epistemic uncertainty estimation. There are two types of uncertainty. Aleatoric uncertainty belongs to the data. We cannot get rid of it, but we can incorporate it into our model. Epistemic uncertainty is the uncertainty associated with the model parameters. Unlike aleatoric uncertainty, we can theoretically get rid of it in the limit of infinite information. Currently, modeling epistemic uncertainty correctly and efficiently is an active field of research, a field that promises to quantify in which situations we can trust and in which situations we cannot trust our model. Our work focuses on providing an efficient estimate for epistemic uncertainty. Recently, much research has focused on scaling reliable epistemic uncertainty estimates to large neural networks. Most notably, stochastic regularization has been linked to variational inference. As such, these type of methods naturally scale to the current training methodologies of neural nets. Therefore, one usually trains a neural network with stochastic regularization, and then at test time, we keep the stochastic process turned on and estimate the variance via several forward passes. However, a remaining downside of this approach is that we still rely on sampling at inference time. We propose to solve this shortcoming by propagating uncertainties using error propagation. When we use stochastic regularization at training time, we place a distribution over the activations of our neural network. If we know the first two moments of this distribution, we can approximately propagate it to the output layer. We propagate the mean using a normal forward path, and then we propagate the covariance matrix using the Jacobian of each layer with respect to its inputs. Note that this is exact for any affine layers, like fully connected or convolutional layers, and only introduces errors at the nonlinearities. However, as you may note, the covariance matrix is pretty large for large activation spaces because it scales quadratically. So we simplify this approach for common vision architectures that repeatedly apply convolutions, stochastic regularizations, and ReLU. We base our simplification on three observations. First, repeated application of ReLU reduces the expected magnitude of the variance. Second, convolutions are local, so they only induce correlations between neighboring activations and only affect a small region of the covariance matrix. And third, noise from stochastic regularization is usually independent. As such, it only strengthens the main diagonal of the covariance matrix. Given these three observations, the variance reduction of ReLU, the local nature of convolutions, and independent noise, we assume a diagonal covariance matrix for these type of architectures. This reduces the computational cost to the one of a normal forward pass. In our work, we mainly apply our approximation to Monte Carlo dropout because this is a very popular method at the moment. We run experiments on UCI regression datasets, train depth regression on Kitty, and semantic segmentation on ChemVid. Here you see our results for approximating Bayesian segnet on ChemVid. Bayesian segnet essentially puts dropout after the central encoder and decoder blocks of segnet. On the left side, you see the original image and the ground truth, and on the right side, you can see the qualitative uncertainty map obtained by Monte Carlo dropout and our sampling-free approximation of it. We further compare the runtime and the uncertainty calibration of both methods. You see the runtime of the sampling-based approach in orange and ours in green. The runtime of the sampling-based approach essentially exceeds ours, surprisingly, after 2 samples. And on the right side, you can see the uncertainty calibration of both methods. we plot the misclassification rate against the quantile of the predicted uncertainty. We see that both methods have a similar calibration, thus we can use them similarly in application contexts like active learning. I thank you very much for your attention this morning, and I hope to see you all at poster number 1.
Thank you. Thanks. Next speaker, please.
Good morning, everyone. This is Hong Liu from Xiamen University. I'm very glad to introduce our work about the adversarial example. This work is done with Pengcheng Lab, Beihang University, Tsinghua University, and Tencent U2 Lab. Recent years, CM models have been shown to be sensitive to the universal adversarial examples, which add a single perturbation to the input image. Therefore, given a CM model and a training set, the algorithm is designed to find a particular perturbation that can fool the CM with high probabilities. There are two kinds of UAP, data-independent and data-independent. The first one is craft UAP using an object function where both the training data, the model architecture, and the model parameters must be known, but it is sensitive to the number of the training samples. The second UAP only needs the model architecture and the parameters, which is more flexible. Due to the lack of input information, we first rethinking this problem by the model uncertainty. We think UAP leverage the uncertainty of a CM model to disturb its output reliability on the input observation. Thus, the key issue is how to estimate such uncertainty, which innovates us to investigate a new method from a new perspective. So this paper, we propose a novel generation method named prior driving uncertainty approximation, which fully utilizes the uncertainty of a CM model. We mainly focus on two types of uncertainty. This figure shows the framework of our proposed method. First, we brief the epistemic uncertainty, which can be computed by the number of active neurons at each convolutional layer. We aim to activate as more neurons at all convolutional layers as possible. This process is done with the sampling method that is to achieve a stable. Second, the electronic uncertainty statics an inherent noise distribution in the input, and we introduce a text bias as the information prior that further increases the model uncertainty. The text prior can significantly improve the performance via our experiments. This uncertainty reflects the influence of the observation noise to the model output, such that different styles of the perturbation will have different attacking performance. In summary, we maximize the active neurons to approximate the epistemic uncertainty and use the text prior to approximate the electronic uncertainty. We further use the Laplacian pyramid frequency model to boost the gradient from the low frequency part, whose output is amplified efficiently to update the perturbation with SGD with moment. We evaluate the proposed method to for a series of CNNs pre-trained on the ImageNet, and we will report the fooling rate results. This slide first shows the attacking performance for data-independent UAPs without training data by direct learning UAP for CNN models. We also show the transfer attacking performance between different CNNs in the table 2. PDUA do help to craft better UAP, which improves the attacking performance. We also compare different perturbation pairs, such as cycle, lines, triangle, diamond, whose results are shown in figure 1. The cycle texture achieves overall the best performance among them. Combining this result with table 1 and table 2, we can conclude that there exists specific semantic bias from the gradient feedback to the perturbation for smaller CNNs, and there exists a more text bias in the deeper CNN models. Oh, sorry. Welcome to our poster. More details and experimental results will be shown. Thank you for listening.
Just a reminder that we'd like to encourage everyone to enter questions at the website sli.do. Thank you.
Next speaker, please. Thank you.
Hi, my name is Ruth. Today I'll be presenting our paper, Understanding Deep Neural Networks via Extremal Perturbations and Smooth Masks. Our work focuses on the problem of attribution, which aims to identify the image regions that are responsible for a model's decision. Consider this classification network, which tells us that this image contains a dog. However, we don't know if the network recognizes the dog image or if instead it recognizes the word dog. Thus, attribution is useful for understanding model behavior. One class of attribution methods is based on backpropagation. These techniques combine network activations and gradients to generate a heat map. They're fast to compute. However, it's unclear what it means when a heat map highlights a region as important. Another class of methods is based on editing the input and observing the effects on the model's output. These techniques are more principled, but they don't consider the full range of plausible occlusions. In our work, we perturb an image by blurring it. Here, the network's response to the bird class rapidly drops as we apply an increasing amount of blur. However, if we preserve just 10% of the image area, then the response is essentially flat. Naturally, this only works for special regions, which we call extremal. To find extremal regions, we learn a mask that perturbs an input and is then fed into a network. We want to learn a mask that is 1, that maximally excites the network, and 2, is subject to a hard area constraint. Optimizing such a hard area constraint is challenging. Thus, we reformulate it as a novel rank-based loss. To do this, we vectorize and sort our mask and then compute the L2 distance between the actual and target distribution of the sorted mask values. Here we optimize for a mask with 20% of its pixels on. In addition to considering masks of fixed areas, we also want smooth naturalistic masks. Consider this toy example of a 1D binary mask. To smooth it, we'd first consider convolving it with a Gaussian kernel. However, this weakens the signal of the mask pixels equal to 1. To solve this issue, we introduce the max convolution operator, which has the nice property of preserving mask pixels equal to 1. Finally, to improve gradients through the max function, we introduce a smooth max convolution, which uses a smooth max function. Here we show how a binary mask is transformed by Gaussian and max convolution smoothing. Notice how the on-pixel intensities are preserved by the max convolution. In summary, we first pick an area and then use SGD to solve the following optimization problem for a large lambda. This ensures that the area constraint is fully satisfied. Finally, we rinse and repeat with other areas and repeat as necessary. Here are a few examples comparing our new method with our prior work that demonstrates our improved stability and sensitivity. Here, our method is able to localize the snake, while our old method yields an unstable mask. The same is true for this freight cart example. Finally, we are now able to capture multiple object instances like these 2 tripods. Our previous method could only capture a single connected component. Here are a few results. Here, we plot the class-specific response of VGG16 in the green bar against the percent of the area preserved. In this manner, we can check what fraction of the input area is actually used by the network to form its output score. In this example, 30% of the area is nearly enough. Our method selects the ostrich bits as expected, and the background doesn't seem to be required. Here's another example. Note that this network is trained for classification and not for image segmentation. For large objects, our method clearly shows that the network only needs to spot a few key details. For instance, we only need to see this monkey's face to max out the output. The rest of its body is not required. In this example, just half of the dog's face is enough to max out the response. We also observe that multiple objects tend to contribute cumulatively to the score. You can see this here as spiders are added one at a time to the image. The response grows monotonically, but not quite linearly. The effect is similar here for these 2 birds. On a weak localization metric called the pointing game, we achieve competitive results. Lastly, we also extend our work to attributing channels at intermediate layers of a network. Recall our original setup for spatial attribution. For channel attribution, we cut a network in half and perturb intermediate activations with a binary vector that effectively drops out whole channels. Like before, we use a rank-based area constraint to encourage the mask to have a certain area, where here area denotes the number of channels preserved. We can visually diff channel perturbations using feature inversion. Here, an input image is learned to match the statistics of the original activations, while another image is learned to match the perturbed activations. Now we can clearly see that the person is deleted from the perturbed activations, while the dog features are accentuated. Finally, we've implemented Rs and other popular methods and benchmarks in the newly released Tortray package. Please visit our poster to learn more. Thank you.
Thanks for the speakers. So please come to the stage. And for any audience who has questions, please go to the microphone. We can start with the question online. So the first question is for the first speaker. How many Monte Carlo samples would you be required to get similar accuracy and accurate uncertainty than with your error propagation?
Yeah, right. So this is a very good question, and also one thing that came up in the rebuttal. We answered this using the UCI regression data sets. So for the accuracy, it's a bit different because we do not alter the mean propagation path. So if we would do that, then probably our method would be as accurate as a bit more Monte Carlo samples, but I can answer it in terms of variance. And so basically after like 200 samples of the Monte Carlo based approach, the variance is roughly as accurate as ours.
Okay, thank you. Any questions from audience? So also there is one question for the third paper. So are the proposed smoothing mask effective on diverse objects, for example, sharper ones?
That's a good question. If you remember the ostrich examples, it really does hug the edges. So especially if we do a more fine-grained sweep of the area, we are able to get kind of the right curvatures.
Yeah. So
a question for this paper as well. Is it possible to apply this technique on the segmentation? No, I think it was for the second. Okay. On segmentation.
Okay. So may I ask a question for the third speaker as well? So because I'm interested in weakly supervised semantic segmentation, so your method seems to be very good at discovering the important object regions. And have you ever tried to do weakly supervised semantic segmentation?
Yeah, so we haven't evaluated on weakly supervised segmentation. Other prior works, such as our first paper, did take a look at this. And what we noted, as well as other papers have noted, is that it's quite hard to get the full body of the object because only the most discriminative parts are necessary. But other works have looked at doing more aggressive occlusions during training. And then when you use methods like ours, then you're able to get more full body coverage.
Yes, thank you. Any further questions from audience? Yeah, maybe.
This one is actually for the third, yeah. Is it?
Okay. Is this for the first one?
Is it possible to apply this technique on segmentation?
Yeah.
Oh, as you.
I think it's the same. Okay, yeah, if we don't have further questions, thanks all the speakers.
And I'll ask the speakers of the next session to please sit on their chairs. Thank you.
Hi, I'm very glad to be here today to present our paper, Unsupervised Pre-training of Image Features on Non-Curated Data. So when we say pre-training, we mean learning visual representations. Indeed, for some years now, a typical setting to solve an image recognition task has relied on two stages. The first one is the pre-training of a CNN on a large-scale supervised dataset, so typically ImageNet. And then the second stage is to use those representations to solve a target task with transfer learning. And the better the pre-training, the better the performance on the transfer task. So this process relies heavily on the use of ImageNet, a large, fully annotated dataset that has been expensive to build. So that's why we want to do unsupervised pre-training instead. So ImageNet is a highly curated dataset composed of carefully selected images that form well-balanced and diversified classes. So simply discarding the labels does not undo this careful selection and only removes part of the human supervision. This is why in this work, we want to pre-train with non-curated raw images from the photo sharing website Flickr. So using non-curated dataset instead of ImageNet without labels means that we have the content of the dataset is very unbalanced with a long tail distribution. It also means that in this scenario, the data comes almost for free, so we can use as much data as we want. So we seek to design a method that works well on large-scale non-curated data. So for this, the method should be robust to a change in data distribution. And for this, we use RotNet, which is a self-supervised technique that manipulates the input data in order to build supervisory signal. Also, the method difficulty should increase with the dataset size in order to really leverage the fact that we have access to more data. And for this, we use our previous work, Deep Cluster, where the different instances of a dataset should be discriminated from one another. So the task of RotNet is to predict the rotation applied to input images. And Deep Cluster is an iterative process where first the representations of a dataset are clusters with k-mean, and then the task of the network is to predict this cluster assignment. And this intuitively becomes inherently more complex if we add more instances and more clusters. So in this work, we propose deeper cluster, which is a mix between RotNet and Deep Cluster. And the clustering part is similar to that of Deep Cluster, except that we're doing hierarchical k-mean because we're dealing with much more data and much more clusters. And then the task of the network is to predict both the rotation applied to the input images and their cluster assignments. So we can look at some results we get with pre-training with deeper cluster. So if we train a network VGG16 on ImageNet classification task from scratch, we would get 74.1 top run accuracy. But then if we do pre-training with deeper cluster on 100 million images from Flickr dataset before, and then we fine-tune on ImageNet, we get a boost of 0.8% in accuracy. So it's a small boost, but it's really interesting to notice that features that are learned in a completely unsupervised way on non-curated raw data allows to improve the performance on ImageNet itself. We can also look at some results with transferring on Pascal VOC dataset. So it's a small dataset with only 5,000 instances, and it's a standard benchmark for evaluating unsupervised representation learning methods. So on the x-axis, we look at the size of the pre-training dataset, and on the y-axis, we look at the performance on Pascal VOC classification task when only the last full layers are retrained and the convolutional layers are freezed. So in red, it's our method, deeper cluster, and in green, it's when we do the rotation task only. So the circle corresponds to training the method on ImageNet without labels, and the cross to using only non-curated data. And we see that it really harms the performance to use non-curated data instead of ImageNet without labels. However, our method is really capable to leverage the fact that it has access to more data. And we see that, interestingly, that between 4 and 20 million of non-curated data are required to match the performance and outperform the performance of the method on ImageNet without labels. So our method also provides a clustering of the pre-training dataset, which is worthwhile for itself. And thank you for your attention.
Next speaker can come.
Good morning, everyone. This is Zhang. I want to introduce the easy-to-use and effective loss function for feature descriptor learning. We study feature descriptor, which is an algorithm that computes a feature vector given an image patch. Ideally, we prefer the descriptor to be robust against various transformations so that we could use it for applications like image matching and retrieval. Conventionally, the descriptor can be constructed based on handcrafted principles, such as aggregated image gradients, but these descriptors require a lot of space to store. Binary descriptors, on the other hand, are efficient to store, but they are less robust compared to real-value descriptors. In recent years, handcrafted algorithms have been replaced by learning-based approaches that leverage image pairs or triplets for learning. Despite it presenting good results overall, obtaining best results requires extensive hyperparameter tuning. Also, there are few solutions that fit both real value and binary descriptor learning. We present a non-parametric loss function that easily works with both real value and binary descriptor learning problems. Our method derives from the classic triple loss function. Given an anchor patch, the basic idea is to minimize distance from the anchor to the positive patch and maximize distance from the anchor to the negative patch, both in the feature space. In practice, it is common to use a margin to prevent learning from being affected by easy training samples. Now the problem is, how should we set a margin? People often use 1.0 as a default value, but is it good enough? Here, for analysis purpose, we evaluate a batch of data using pre-trained HeartNet model. The horizontal axis represents D positive, whereas the vertical axis represents D negative. A triplet is within the district boundary as long as D negative is larger than D positive. The triplet loss simply pushes all the points toward top left corner. Interestingly, we found that a margin equal to 1.0 isn't effective at all, because there's a point about that. In contrast, a value like 0.375 seems more reasonable. The blue points are ignored by the network, and the green points are used for training. A limitation of triplet loss is that it only relies on hard margin to make a binary decision whether triplet should be used for backpropagation. Also, the margin stays unchanged throughout training, which means that we need to guess how the training progresses beforehand. We call this conventional margin as a static hard margin. Come on. We can make the margin soft by using a handcrafted function like a soft plus. Harder triplets are designed with higher weights than easier triplets, but this function is still static throughout training. Alternatively, we could make the margin dynamic by always using the hardest n triplets to do backpropagation, but any triplet that is just slightly easier is completely excluded. So this is again a form of hard margin. Our solution is to use a dynamic soft margin. The idea is that during training, we build a moving probability density function of D positive minus D negative, which is correlated to how hard the triplet is. We can integrate a PDF to get a cumulative density function. We then simply look up the corresponding CDF value to weight the triplet. The harder triplets always correspond to higher CDF values, whereas the easier triplets correspond to lower CDF values. For example, if a triplet is mapped to 0.5 on the CDF, it means that it's likely to be harder than roughly 50% of triplets we've ever seen. So we could set the weight of triplet to be 0.5. In short, our soft margin strategy always takes current training progress into consideration, and more importantly, we don't need to pick any parameter for this loss function. Here's a video that demonstrates how the PDF and CDF evolve during training. The points are pushed toward top left corner, but none of them can surpass a hard margin of 1.0. To form the triplets, we adopt the simple hard margin strategy used by HeartNet, which leverages the property that the Euclidean distance between two unit-length descriptors can be efficiently computed using a single dot product. We made simple modifications for learning binary descriptors. We first binarized the network output using the hyperbolic tangent function, and luckily, the Hamming distance between two binary descriptors can also be efficiently computed using a single dot product. When we use the conventional triplet loss, there exists a sweet spot when we vary the margin for both real value and binary descriptor learning. In contrast, our method leads to the best result in both cases without having to select that parameter. We have also achieved the competitive results on popular benchmarks such as edge patches. Please refer to our paper. Thank you, and please come to see our poster as a number 5.
Hi, my name is Min-Young Kim. I will present the Bayes-Factor-VAE, a new hierarchical model for factor disentanglement. So we are interested in unsupervised representation learning. For instance, given the data of unlabeled face images, we like to achieve two things. First, build a latent space that explains the variability of the data, but in such a way that the factors are disentangled. This means that when we change one factor while freezing the others, we get variation in only one aspect in image X. In this example, those factors could be expression, gender, and pose. Second, we like to discern relevant factors from nuisance. A factor is called relevant if it is statistically dependent on image X. It is nuisance otherwise. So in this example, nuisance might be independent noise in face images. So how do we accomplish this? So we first need to choose the model for our data. So we follow deep latent variable model of the VAE class. In VAE, the latent prior is fixed as standard normal. Changing this will be critical to our new model, as I will explain shortly. First, to fit the model to data, we optimize the variational lower bound that consists of two components, the reconstruction loss and the divergence from the prior. Our second goal is the disentanglement of factors. We can achieve this by making the variational prior Q of Z fully factorized. One way to do so is by minimizing the total correlation, or TC. This leads to a new objective, which now includes the disentanglement. Our third goal is the separation of relevant and nuisance variables. We quintessentially choose the dimension D of Z large enough to cover all factors. Among those, some will be relevant, related to true factors, but others may only serve as conduits in data generation process. Motivated by the semi-parametric ICA, we consider to learn the latent prior P of Z directly from the data. So here, two key elements stand. The nuisance variables need to be standard normal. However, for relevance, the priors had better be non-Gaussian, learn to become statistically dependent on the input. There are many possible choices of non-Gaussian priors for relevant factors. Here we adopt a simple Gaussian prior, but let the precision parameter alpha be flexibly chosen. So we propose three models. The first, BFVA0, we treat precision alpha as the variables to be learned. And in VFVA1, we replace the point estimate with the hierarchical gamma prior and infer the posterior. And finally, in BFVA2, we introduce relevance indicator variable R to directly learn whether a factor is relevant or not. So for 5 benchmark data sets, our models achieve the best scores, best performance. So here we used 3 disentanglement metrics. We demonstrate our model using traversal over latent factors on the 3D face data set. Ideally, traversing one factor at a time should result in only one aspect of the data changing. So we see that the identified factors shown in red and blue boxes correctly correspond to true factors. Another key benefit is that we can control the cardinality of the relevant factors. We do so by the regularization parameter eta. On CellLab A dataset, here the strong factors on the left panel correspond to gender, azimuth, etc. can be detected regardless of eta. But weak factors are only detectable when eta is small, shown on the right, with factors such as smiling, sunglasses, and others. So for all technical details and results on our Bayes-Factor-VAE, please visit our poster, paper ID 4549 and poster ID 6. Thank you.
Thank you very much. May I also speaker come to the stage, please? You can. Okay, so we'll start our Q&A now. Please come to the microphone if you have any questions. So there are questions for the deep cluster paper, deeper cluster. Okay, there is a question from the audience. First, maybe.
Thank you. I have a question for the second speaker.
Okay.
And the question is, if you compare to noise contrastive estimation, for which, you wouldn't have to set a margin as well.
To repeat the question?
Have you compared to NCE, noise contrastive estimation?
I'm not familiar with the topic. Could you elaborate?
So in NCE, you would use a log loss, right? And so you would contrast your positive pair against a bunch of negatives, but you would send the scores through a cross-entropy loss.
Basically for descriptive learning, the most popular approach is use triple loss, but we just want to solve the problem that we have to pick that margin to achieve the best result. So we haven't really compared to other branch of loss functions.
Okay, thank you.
Yeah.
Okay, so the question for the deeper cluster paper, so was why do you, so how do you decide the number of clusters for unsupervised pre-training first?
So the number of clusters is just a hyperparameter of our method. So in order to select all the different hyperparameters, so the number of clusters, the learning rate, and so on, we use a downstream task to evaluate the features that we get. So in particular, we use the transfer on Pascal VOC classification task when only the last fully connected layers are retrained and the convolutional layer are freezed. And so the choice that we did according to this criteria was to use like 320,000 clusters in total.
Okay, and the second question was, why do combining clustering and rotation helps? Does cues for rotation differ from different clusters and that helps the representation?
So the idea of the paper was really to combine the cues from self-supervised learning, where we use a pretext task to learn features, and the cues of clustering, where we try to find the latent concepts not present in a dataset. So, yeah, and those are like different paradigms. For example, the rotation, it doesn't really rely on the underlying structure of the dataset. It's really a task that is at the image level. So we hoped that it would be kind of robust to a change in the data distribution that we have, like with the very unbalanced distribution of Flickr dataset and the balanced distribution of ImageNet. And we were hoping that the clustering part would leverage the fact that we have more data, because if the dataset size increases, the deep cluster, the nature of the deep cluster task really becomes more complex because you have to discriminate between more images and more clusters.
Okay, thank you.
Yeah, due to time limitation, let's thank the speakers again and invite the next speaker to come. For the next three speakers, please sit in the waiting area. Thank you.
Hello everyone, I'm Zhang, a PhD student from the University of Victoria. I'll present our work on linearized multi-sampling for differentiable image transformation. This is a joint work with Feiyue, Andrea, Edward, and Huang. I'll start with an example. In this example, we try to find the parameters defining an image transformation given the source and target image, as shown here. We do so by computing the pixel level difference using the L2 distance and calculating its derivatives with respect to the warping parameters and directly optimizing them. The two results shown here are from the bilinear sampling and our sampling method. We use the same optimizer and the learning rate, and the only difference between the two optimization processes is the differentiable sampling method. As shown, bilinear sampling fails in this simple case, while our sampling method succeeds. This limitation of bilinear sampling is often overlooked in the literature, although it can make a big difference. To understand why this happens, let's first recap the basics of bilinear sampling in the context of deep learning. To sample an image, first, we create a sampling grid with a certain resolution. Then, we transform the sampling grid to the input space given transformation parameters. For example, translation, rotation, and scaling. For each sampling point, we find its four nearest neighbors and sample the intensity based on bilinear interpolation. This, in fact, can cause some problems. Let's take a close look at a single sample in the output space. We first transfer the sample to the input space. Then we do bilinear interpolation and assign the value. Bilinear sampling works fine if the output is at the same resolution as the input. However, when severe downsampling is applied, the gradients are no longer representative. For example, as shown here, the gradients will only backpropagate through the 4 pixels in the original input, and the gradients with respect to the warping parameters would only come from those, which is not good. We propose linearized multi-sampling as a differentiable alternative. Our method improves the quality of gradients by doing the linear approximation at the sampling center with a transformation-aware receptive field. First, we generate random auxiliary samples around the center point. We then transform them to the input space and get the intensity of each auxiliary sample. Then, we do a linear approximation at the center point. Mathematically, this boils down to this equation. Here, the left-hand side is the linear approximation at the center point. The first term of the right-hand side is the intensity at the center point. And the matrix A is the linear approximation coefficient we are seeking to find. Solving this equation is straightforward. We're calculating the matrix A by applying the pseudo inverse. Since the auxiliary samples now correctly cover the correct region in the input image, the generated gradients should be more representative. To see how this affects the actual gradients, we visualize the gradient directions. We translate the cat image to different locations and visualize the gradient with respect to the translation parameters by computing the L2 distance between the translated and the original. In other words, we try to drag the translated image back to the center. Therefore, the ideal gradient direction should always point towards the center of the original image. Here is the actual gradients visualization of bilinear sampling and our linearized multi-sampling. We can see our method provides much more robust gradients. This also affects the performance of spatial transformer network. We apply our method to classify traffic signs. Here, we use a spatial transformer to predict the warping parameters of each traffic sign and a single network on top to classify. As shown in the table, our method improves the classification accuracy at all downsampling rates. It outperforms the bilinear sampling by almost 5% accuracy when we have downsampling rate as severe as 8 times. Thank you for your attention, and please come to our booth 7 for more details.
Next speaker, please.
Good morning. Today I'm going to talk to you about ADA transform and adaptive data transformation method. I'm the last speaker due to visa issues with my other students. So the motivation is as follows. Like, training data cannot cover the variance of the test data, as you all know. The goal is to improve the robustness of deep models. The two trees, as you see here, can have two similar shapes. Meaning that the training and test data have similar distributions. And the leaves on the right tree represent the variations in data caused by perturbations. And the goal is to train models on the limited training data set on the left and test on the perturbed data on the right. Okay. Data augmentation is very useful, of course, to train deep models because due to the plague of annotations, etc. So Auto-Augment was a very nice paper that appeared last summer, and it was designed to improve the generalization of the standard data sets, but was not designed for robustness purposes, as I'm going to explain to you later. So the goal of this paper is to two things. First, well, like what every other method does, to increase the data variance in training, but at the same time, decrease data variance in testing. This is very important to improve for robustness. So one is basically the competitive training, which is basically increase the variance, while the other one is the cooperative testing. So these two parts of the network, as you're going to see later, are important. So the solution is you're going to have a competitive task, which have three components, the transformer, discriminator, and the target network. And the data will go through the transformer and then be fed in the target network. Okay, so in the cooperative training, the transformer receives supervisions from both the target network and the discriminator. Discriminator learns to increase the loss of the target network, hard transformations, and at the same time, it also tries to make the transformation data be realistic. And the discriminator learns from both the original and the transformed. So in the cooperative task, we use the transformer to win the target network. The transformer learns to decrease the loss of the target network by generating easy transformations, small scale perturbations. So if you see the solution, then it has two components. So the whole framework, so you jointly optimize the three components, the transformer, discriminator, and the target network. And the optimization will alternate between the competitive training and cooperative testing. So the transformer uses meta augmentations to perform incremental transformation. We follow the work in one here in reference one, defining some small transformations, the meta transformations, like swirl, rotate, etc. Transformation is divided into several steps, and in every step, the transformer is conditioned on the transformed image to the previous step. We want to show you some results on the robustness. First is about geometric transformation, scaling and rotation. It's designed for large scales and rotation. We do a lot better if you see on the two slides here on the left, and on the right, you would see about the error. Now, how about besides the special perturbation, what's this on texture? So for both clean and perturbed data, the method that performs the baseline, and more importantly, the performance on the perturbed data is larger. This means that the method is more robust against texture perturbations. And then there's more testing, which is 100 times faster than Auto-Augment. Shows you the speed, even though we're a little bit worse in terms of accuracy, but we are a lot faster. Finally, how about qualitative results to understand how this thing works? So these are on the top is the original testing, while on the bottom is the transformed. So basically it helps you zoom in the data where you saw that improved during testing the performance. Thank you, and if you have any questions, please do later.
Good morning, everyone. I'm Jiaqi Wang. Now I will present our paper, Craft Content-Aware Reassembly of Features. Feature upsampling is a key operation in a number of convolutional network architectures. For example, LPN in object detection, Hourglass in pose estimation, PPM in semantic segmentation, and UNet in image synthesis. Its design is crucial for dense prediction tasks. There are various upsampling operators. Among them, nearest neighbor and bilinear interpolations are most widely adopted. Deconvolution and pixel shuffle are also commonly used upsampling methods. Although widely adopted, those methods have some drawbacks. First, they use content-unrelated kernel. Interpolations use handcrafted upsampling kernel, and the other two methods use shared upsampling kernel across different locations. Second, the recipe field of those methods are limited. Interpolations only support subpixel neighbors, and the other two methods have limited kernel size. Third, since deconvolution and pixel shuffle need to perform deep convolutional layer, they will bring heavy computational overhead. In this work, we propose content-aware reassembly of features graph. Graph has several appealing properties. Content-aware handling. Graph enables content-aware handling which generates adaptive kernels on the fly. Large field view. Graph can aggregate contextual information within a large recipe field. Lightweight and fast to compute. Graph introduces little computational overhead and can be integrated into modern network architectures. The figure shows the framework of Graph. Graph has two modules, kernel prediction module for content-aware handling and content-aware reassembly module for large field view. In Graph, if we wish to upsample a feature map, we need key-up by key-up content-aware reassembly kernel for each target location. To predict such kernels, there are three sub-modules in kernel prediction process. Channel compressor, it will compress the input feature channel from C to CM. The goal of this step is for speed up without harming the performance. Content encoder is one convolutional layer with kernel side key encoder to generate reassembly kernels based on the content of the input features. Kernel normalizer, each key-up by key-up reassembly kernel is normalized with a softmax function. After predicting the reassembly kernel for each target location, the content-aware reassembly module will use such kernels to upsample the feature map. This module will extract the key-up by key-up nearby region of a location and the corresponding reassembly kernel. The extracted features will be reassembled by the kernel. By this way, we get a feature vector on one target location. We will perform this process on each location, and finally, we get the upsampled feature map. Due to the large key-up by key-up reassembly kernel, the upsampled feature map will have large field of view. Graph can be inserted into existing frameworks with upsampling operators. On object detection and instance segmentation, we use faster RCN and mask RCN as baseline method. Graph is adopted to LPN and masthead. On semantic segmentation, we choose ARPANET as the baseline. Graph is adopted in three different modules. They are PPM, LPN, and multi-level feature fusion. On image painting, we choose global and local and partial count as baseline. We replace the original upsampling methods with Graph. Graph shows consistent gains across object detection, instance segmentation, semantic segmentation, and image painting with negligible computational overhead. But how does Graph work? In LPN, a pixel in the upsampled feature map resembles information from a larger region. Graph tends to capture the information according to the shape of the object. The final feature map is much sharper and clear. And finally, Graph also brings better instance segmentation results. In summary, Graph has three advantages. Universal. Graph can be inserted into different architectures as upsampling operators. Lightweight. Graph is fast to compute and parameter efficient. Effective for dense prediction tasks. Graph improves the performance of mainstream methods in various dense prediction tasks. Our code is now available on MM detection. Happy to see you in the poster session. Thank you.
Yeah, please, the three speakers, please come to the stage, and it's a question and answering session. So for the audience, if you have questions, please go to the microphone. Maybe we start with some online questions. So the first one is for ADA transform. And adversarial models and reinforcement models are often hard to train. How much sensitive is this model to training details?
So the question was for ADA transform. Adversarial models and reinforcement models are often hard to train. How much sensitive this model is to the training details?
It's a lot faster and easier to train with this method.
Okay, you didn't experiment.
100 times faster than the previous methods. And not only, but so the trick is that not only it augments during training the data set, but also shrinks the variance during testing with this cooperative and adaptation that we do between the both parts of the network.
Okay, thank you. And for the first presentation, is it possible to exchange IC STN to STN after training to improve inference time?
To improve the inference time, our method is more about the sampling method, not about the architecture. And our method has overhead about 50% slower. So I don't think it can improve the inference of ICSTM.
Okay, thank you. And also a question for ADA transform as well. And only discrete meta value cause the experiment on the paper. How can this model be adopted to continuous meta value kits?
I think that I can answer later
Okay.
to the individual person.
Okay, thank you. And,
Hi, hello. I have a question for Jiaqi. So how is graph compared to deformable convolution in terms of the ease of use and the concept?
Yeah, okay. I think there are three differences. First of all, that graph is not a convolution operator. However, deformable convolution, so it's a convolutional operator. And the second is that deformable convolution, that it will extract information from the spatial sampled points. And our method is the weighted, you can consider as a weighted combination of the feature reassembling inside the local region. And the third difference is that our graph is much more efficient than the deformable convolution. And I think this is the differences between the deformable convolution and our method. Thank you.
Would you comment a little bit on the difference of efficiency and why there is a divergence?
The efficiency? The deformed convolution is a convolution operator, so it will calculate a very large matrix multiplication, matrix multiply, and our method is just a spatial weighted sum of the information in a local region. So our method is much more lightweight, and also the weight predicted in our method is shared across different channels. So this is also help our method is very parameter efficient, not only in the flops but also in the parameter.
Thank you.
Thank you.
Thank you very much. May the next speakers come to the stage. Thank you.
Good morning, everyone. I'm Dou Quan from Xidian University, China. It's my honor to have this chance to give a presentation on our work, aggregated feature difference learning for cross-spectral image patch matching. Cross-spectral images have complementary information. While before using their advantages, we first need to build a corresponding between image patches. However, there are many challenges, such as illumination changes, rotation transformation, viewpoint changes, and a significant appearance difference between cross-spectral images, which need more invariant and discriminative features for robust matching. There are two classic deep learning-based matching methods. First one, descriptive learning methods focus on learning high-level features and measure their similarity based on their feature distance. Another method, metric learning methods, transform matching tasks into a binary classification problem, matching and non-matching. However, both of them ignore the discriminative information in low level and middle levels, and not compare the feature correlation of each level. In this paper, we propose an aggregated feature difference learning network, different from existing methods only focus on learning high-level features. AFDNet can aggregate discriminative information from multi-level features and predict matching labels based on feature difference rather than features. Because feature difference can conceal the same signal of matching samples, but amplify the different signal of non-matching samples. This presentation is about the detail of our proposal. First, extract multi-level features from image patches. Then, compute feature difference of each level. Next, aggregate feature difference from multi-levels. And finally, predict matching labels based on the aggregate feature difference. To evaluate our proposal, two datasets are adopted in our experiments: a cross-spectral image patch matching dataset and a single spectral image patch matching dataset. We adopt LPR95 as evaluation metric, which means the smaller the value is, the better the matching performance is. Experimental results demonstrate that our method achieves the state-of-the-art result and boosts the matching performance by a fairly large margin on cross-spectral image patch matching, and achieve a competitive result on single-spectral image patch matching. In order to find the best aggregate network, we compare the performance of AFDNet with varied configuration of aggregation, which aggregate feature difference from different number of levels. AD0 means without any aggregation. Its performance is the worst on all test datasets, so aggregate feature difference can boost the matching performance. And when the feature difference from the last three levels are aggregated, its performance is the best on average. In order to remove the influence of cross-spectral image patches, AFDNet combines the instance normalization and batch normalization, which has a better matching performance and a faster convergence. In conclusion, aggregate feature difference network learns more discriminative features for image patch matching task. And we find that feature difference is a special case of feature correlation. We are going to study more general feature correlation learning method for matching. That's all. Thank you for your attention. Welcome our poster.
Well, hello everyone. Today I'm so glad here to introduce our paper, Deep Joint Semantic Reconstruction Hashing for Large-Scale Unsupervised Cross-Model Retrieval. All authors are from Peking University. The goal of cross-model hashing is encoding the multi-median data to a common binary hash space. In such space, the correlation among the sample from different modality can be effectively measured by their Hamming distance. So, the latent semantics among the different modalities is a key point. Specifically, in our paper, we focus on image-to-text cross-model retrieval. The illustration is shown in the bottom part. Reviewing the progress of cross-model hashing this year, to learn better binary code B, one common framework is represented as equation 1 and is implemented by the graph Laplacian matrix. However, after our analysis, there are mainly two underlying problems. First, these frameworks use two terms, SI and ST, to individually perceive the neighborhood structure information. And second, this framework is unsuitable to the bench-wise network training minors because the trace form merely constrains the binary codes to perceive the original similarity order. Based on the above problems, we propose DJSRH, Deep Joint Semantic Reconstruction Hashing. There are mainly three stages in the whole pipeline. We first propose joint semantic excavation and the left part, which makes it highly competent to capture the latent semantic affinity among the input instance. Then, we code each instance into a common hash space and the right part. Finally, both the text network and the image network are loaded by our proposed reconstruction frameworks batch by batch. In the following page, we will explain the excavation and reconstruction part in detail. Excavation part, constructing the joint semantic affinity matrix S, we first match the information from different modalities to refine each other, which is represented as equation 2. Then we add high-order information to further excavate the semantic instruct relations, which is shown as equation 3. So, the proposed joint semantic matrix S refines the affinity relations from different views, SI, ST, and the high-order neighborhood description. The next is the reconstruction part, reconstruction with the binary code. As mentioned above, the trace form of graph Laplacian matrix just perceives the similarity order in batch minors. So in our proposed reconstruction framework, it drives to reconstruct the specific similarity value instead of the similarity order. So to regularize a better quantization range of S, we also add a linear transformation parameter mu. Furthermore, we also consider the intramodal reconstruction of image and text. So the final training loss function becomes to equation 5, which is more suitable to batch-wise training networks than the common Laplacian method. Then is our experiment part. We compare DJSRH with sex representative baseline. The former four are shallow methods, while the last two and ours are deep methods. From the table, our method can achieve significant improvements on 3 benchmark datasets. To further verify the impact of each component in DJSRH, we designed several variants to evaluate the performance when adding the proposed components one by one. From the table, we can observe that each of our components can play a certain role for our final results. Last but not least, we would like to highlight that the simplest variance, DJSRH1, has surpassed UDCMH, the best method shown in the last table except ours. That's all of our presentations. Thanks for your listening and coming. If you have interest in our papers, please come to our poster number 11. Thank you.
Hello to everybody. My name is Stanislav Morozov. I work in Yandex Research, and now I'm going to tell you about unsupervised neural quantization for compressed domain similarity search. In this work, we tackle the problem of unsupervised visual descriptors compression, which allows efficient similarity search over a compressed database. First of all, we consider billion-scale collections of high-dimensional vectors, which we compress to several bytes per data point. Our evaluation measure in this setup is recalled K. Currently, the dominant unsupervised compression methods belong to the multi-codebook quantization paradigm. In this paradigm, descriptors are effectively approximated by a sum or a concatenation of few code word vectors coming from several disjoint codebooks. Most of the quantization techniques work in a symmetric search scenario, that is, don't compress query vector, which provides higher retrieval performance. Fast distance computation for quantization methods becomes possible via the usage of lookup tables. One of the most known quantization techniques is product quantization. Product quantization encodes each vector as a concatenation of M code words from M codebooks. That is, product quantization decomposes the original space and is the product of M subspaces and quantized subvectors in each subspace. Another approach, additive quantization, is more general. It represents the vector as the sum of code words. However, the computation of the optimal additive quantization is an NP hard problem, and its usage is connected with many optimization difficulties. We propose unsupervised neural quantization, an unsupervised compression scheme for the problem of compressed domain retrieval. Our architecture consists of two main parts. The encoder maps the data vector into a tuple of discrete codes, and the decoder reconstructs the original vector from its compressed representation. In the encoder part, we use a simple feed-forward neural network with M output heads which are trained jointly. One can think of encoder as a mapping of data vectors and a product of M learned spaces. Each of the spaces in this product possesses a code book, and we assign data vectors to discrete codes based on the dot product in the learned space. To make our encoder differentiable, we use Gumbelsoft's max trick. Then we feed the discrete representation into the decoder, which is another feed-forward network that sums the corresponding code words and reconstructs the vector in the original data space. During the retrieval, we use two-stage nearest neighbor search and two different definitions of distance functions to provide both high compression accuracy and efficient retrieval. In the first stage, we select the set of promising candidates using the distance function, which allows for an efficient search algorithm via lookup tables. In the second stage, we rank selected candidates by reconstructing vectors with more expensive but more accurate decoding procedure. We train our model by explicitly fitting the two distance functions to maximize recall. The first distance function is defined in the original data space and can be trained with Auto-Encoder-like objective. However, there is no guarantee that minimizing this objective would result in good candidates being selected for the ranking stage. Therefore, we employ a metric learning approach by minimizing the triplet loss in the learned space. Finally, we add a regularizer for Gumbelsoft Max that encourages equal frequency of code words. Following the most of the recent work on unsupervised quantization, we perform the experiments on two datasets. Deep1B, which consists of visual descriptors that are computed from the activations of a deep neural network, and Big ANN1B, containing histogram-based SIF descriptors. We compare the proposed UNQ method with the current state-of-the-art approaches for the unsupervised compression problem. One can see that the proposed UNQ method outperforms the competitors in most operating points. In particular, it always works better for 16 bytes encoding and show descriptors from BKNN1B dataset. Thank you for attention. If you are interested, you can find me in the poster session, poster number 12.
Thank you very much. Can all the speakers come to the stage for the Q&A? Thank you. Any question in the room? Okay, we can start with a question from the website. So it's for paper number 2, the deep join semantics. What is your insight into using different types of CNN descriptors before binarization? For instance, the captioning net for hybrid representation.
Sorry.
He was asking what was your insight in using the different types of CNN descriptors before binarization, for instance, the captioning networks for hybrid representation?
Since we think the difference between the image and text, so we need to use two separate networks to deal with two kind of data set. So separate networks can maybe get better performance.
I also had a question. I noticed you used different parameters for the different loss, inter and intra reconstruction loss. And since the parameters delta 1, delta 2 need to be chosen differently for the different data sets, do you have an heuristic to set the different parameters like beta and these lambdas?
Actually, during our experiment results, for different data sets, we don't have some insight about how to train the parameters. Just try all the choose and select the best one. Yeah.
Okay. One question for the last speaker. Can you elaborate on the diversity regularizer for the Gumbelsoft Max, please?
Can you repeat the question, please?
can you elaborate on the diversity regularizer for the Gumbel softmax?
We used a coefficient of variation regularizer, and exact formula are presented in the paper, and you can get some details in the poster session. But the regularizer was called the coefficient of variation. It's not our regularizer. It was taken from another paper.
Okay. Maybe I have a question for the AFD net paper. Could you tell which component of the approach has a larger impact on the result? I saw briefly batch norms, normalization choices, batch norm, instant batch norm, and softmax. Could you tell what was the most bringing most significant gain to the?
Oh well, because we're working on the cross-spectral image matching, so the information from the different domain. So that's the reason we use instance normalization, but that costs a lot of computation. So we integrate the instance normalization and batch normalization together to keep the to extract the share the feature from the different domain and maintain the faster convergence. Yes.
Okay, thank you.
Thank you very much. Let's thank the speakers again.
Next speaker, please.
Hello everyone, I am Somava Kumar Roy from Australian National University. I am here to present our paper titled Siamese Network, The Tale of Two Manifolds. This was a joint work undertaken by me, Mehta Sharandi, Richard Nock, and Richard Hartley. In this paper, we propose and develop two Riemannian geometrical configurations for learning a rotation invariant metric that is such that the embedding is rotation invariant. So on the right of your screen, you can see a general Siamese network. It consists of two CNN streams which share with theta. The metric M is used to learn a Mahalanobis metric between the two embedding points x and x tilde. For a varied distance, M should be a positive semi-definite matrix, and which can be decomposed as LL transpose, L being a tall matrix of size NP. With such factorization, we can learn L to be a separate embedding layer in the Siamese network, such that the properties of a metric is kept. So what is the problem with Siamese network? We have M as LL transpose. However, if L is multiplied with any rotation matrix R, we obtain the same M, as shown in equation number 3. As a generalization, let us consider minimizing a function in 2D space for a given value of L and a given value of L. For different values of R, we obtain the same L, which results in a circle. And for different values of L, the search space then becomes concentric circles, as shown here. However, if the function is rotation invariant, then the search space is simply the real line and not the entire R2, thereby reducing the search space from R2 to a simple straight line. So in one of our solutions, what we propose is we decompose M as U, UD transpose, which is further decomposed as U D half transpose U transpose. And L is then U D half, which is the Stiefel solution proposed in our paper. Therefore, the Siamese network shown here transforms into this, where U is a Stiefel layer consisting of fully connected layers with orthogonal columns. And in our paper, we also produce an additional manifold called QConf, which is presented in the paper. However, to preserve the properties of U, we invoke stochastic optimization operations on Riemannian manifolds, and we augment the same operations in the RMS prop optimizer. In the next slide, I will just give a brief descriptions of the manifold operations that we have used. Any 2 point in a manifold is connected by the shortest path, which is known as the geodesic. It is equivalent to a straight line in Euclidean space. Every point on a manifold has a tangent space associated with it, which consists of all the tangential vectors at that point to the manifold. After backpropagation, we obtain the Euclidean gradient shown as delta J here, which is projected to the tangent space using the projection operation. From the projected gradient, we use the retraction operation to obtain the retracted point, that is R, shown in the figure. In order to add 2 vectors on the manifold, one of the tangent vectors must be parallelly transported to the tangent space of the other point, and we use the parallel transport operation for that. So we invoke these properties into the single layer neural network. We have trained it on the MNIST dataset for 3 configurations: conv, qconv, and Stiefel. As observed, qconv and Stiefel have much compact clusters in the embedding space compared to conv, while obtaining lower top-on error rates. We also perform deep metric learning experiments on CUBS and CARS dataset. Here I have shown the results only for CUBS datasets against 2 baselines, but just by incorporating these geometrical properties, we obtain significant improvements over the baseline in terms of NMI and R1. It is to be noted that we have only trained using the triplet loss in our experiments. We have also shown improvements over the 2 recent deep generative based models. You can also refer to our papers and our poster for more details. Thank you.
Hello. Today I'll talk about learning deep embedding networks for graph matching. I'm Rongrong from Shanghai Jiao Tong University. So firstly, let me briefly introduce some background knowledge of graph matching. So graph matching is a long-standing problem in computer vision and pattern recognition. While in computer vision, graph matching finds the node-to-node correspondence of multiple graphs utilizing the graph structures. And in graph matching, we consider both node-to-node similarity and edge-to-edge similarity. By jointly maximizing the node similarity and edge similarity, the graph matching problem is mathematically formulated as an optimization problem, as shown by the complicated one on the slides. A more generally applied formulation is based on the so-called affinity matrix. The affinity matrix K is a matrix with quadratic complexity, and it encodes both node-to-node similarity and edge-to-edge similarity. So the affinity maximization problem mentioned before is equivalent to the so-called quadratic assignment problem, or QAP in short. It is NP-hard. While previous research works mainly focus on approximately solving this QAP problem, while in this work, we propose a deep embedding network to tackle this graph matching problem. And graph embedding networks owns the capability to embed graph structure, including nodes and edges, into node embedding vectors. So in this way, graph matching can be evaluated between 2 node embeddings. And therefore, we can simplify the NP-hard QAP problem into a solvable linear matching problem. So let's take a brief look at our proposed approach. Firstly, given 2 images with key points, we feed it into a CNN, and we get 2 graphs with features. And by taking graph convolution and cross-graph convolution accordingly, we encode both node similarity and graph similarity into the embedding vectors. And finally, we solve the matching problem by synchron algorithm and obtain the matching results. So to highlight our contributions, we are the first end-to-end solution in graph matching incorporating embedding. And we simplify the NP-hard QAP into a linear problem by using embeddings and the linear problem is solved exactly. And finally, we propose a combinatorial permutation loss for end-to-end training. Well, firstly, we extract CNN feature for key points in the images. And graph convolutional networks embeds graph structure information into these node embeddings. And our proposed graph convolution is mainly inspired by the popular and well-known GCN. And each node is updated by its adjacent nodes, and we enforce weight sharing among all nodes. We further devise a cross-graph embedding network based on graph convolution. So in the cross-graph convolution, features are aggregated from nodes with similar features among multiple graphs. And cross-graph convolution further improves the performance of our methods. After obtaining node embeddings and their similarities, we adopt a synchrony algorithm to solve this problem. So in synchrony algorithm, given any non-negative square matrix, by iteratively performing row normalization and column normalization, the matrix finally converges to a so-called doubly stochastic matrix. So for a doubly stochastic matrix, each column and each row all sums to 1. And synchrony algorithm is fully differentiable and is appealing to end-to-end deep learning training. So finally, we propose a permutation loss based on cross-entropy for end-to-end training. So compared to other loss functions in pure methods, we argue that the permutation loss meets the combinatorial nature of graph matching. And finally, our evaluation on both synthetic dataset and real image dataset shows the superiority of our methods. And our code is available online, and you may scan the QR code. Thank you.
Good morning, I'm Zhang Huang, and I will talk with you today about the Functional retrieval by graph reasoning network on similarity pyramid. This work is co-operated by Zhang Huang, Yiming Chen, and Wei Zhang from Stan, Yiming Gao, Guanbin Li, and Liang Ling from Sun Yat-sen University, and Pin Luo from the University of Hong Kong. Previous method newly computed global similarity between the query and the gallery. They first extracted feature maps and get feature maps x and y, which are average put into the global features ax and ay. Finally, the similarity is computed between the two global features. In most cases, the global similarity between x and ay is approximately equal to the sum of local similarity between all possible pair combinations of xi and yj. One drawback of the global similarity is that it's very easy to introduce a noisy singulars. The global similarity might introduce noisy due to the occlusions, wheel changes, and cutter background indicated by the red rectangle. For example, the upper part of the query is occluded by the hands and the mobile phone. It might also introduce noise due to misalignment between the two local features, as indicated by the blue rectangles. For example, the similarity between the upper part of the query dress and the lower part of the gallery dress. So, our work attempted to address the above issues from two dimensions. First, we compute the local similarity from multi-scale. Our redefined similarity S-prime is approximately equal to the local similarity between the query and the gallery, plus the local similarity between all possible local region pairs at scale 2 and the pairs at scale 3, and so on. Second, instead of equally treat each local similarity, we learn a weight for each local similarity. For well-aligned pairs, we would like to increase their weights as shown by the red rectangles. For misaligned pairs, we would like to decrease their corresponding weights as indicated by the blue tangles. We propose an end-to-end network named GRLED to achieve the two goals. Give one query and gallery pairs. Their features are extracted in the feature extraction modules, which are fed into similarity computation modules to build a similarity pyramid graph with all region pair similarity being the graph nodes. In the similarity computation modules, XIL is the ith-look feature of the query at scale L, while YJL is the jth feature of the gallery at scale L, and SIJL is their similarity vectors. Further, the global and local similarity are propagated and updated in the similarity reason modules. It finally output whether the input image pair belong to the same clause or not. So, the loss function of our network is the cross-entropy classification loss. Our proposed GRLED outperforms previous method with impressive margins on deep fashion. Particularly, it even performs better than all the variants of VAM, which use closest mask to train the segmentation mask to ignore the cutter background. Specifically, it absolutely improves the top 1, top 20, and top 50 accuracy of the best ever reported result by 12%, 21%, and 19%. We also compare them on 3-2 shop dataset. GRLED performs best on all subset of 3-2 shops, namely tops, dresses, skirt, pants, and outerwear. We visualize the important regions which contribute greatly to the further similarity. We find that our GRLED can automatically find the thinnest common regions between the query and the gallery, as shown by the left figures. Besides, we found that it can focus on the local similarity between discriminative local region pairs after graph reasoning, as shown by the right figures. Thank you. For more details, please visit our poster.
Other speakers, please come to the stage.
And we'd like to ask you to remain seated to show respect to the speakers and allow the Q&A.
Okay, thank you. And so is there any questions from the audience in the room? So maybe we can start from one question online. So this is for the last speaker. So how do we define and retrieve the scale for an image?
We just define the scale manually. For example, we split the image into 3 by 3, 3 by 1 grid, something like that.
Okay, thank you. So I have one question for the first speaker. So I noticed that in the last slides you show in the experiments in the CDF-Based dataset, it achieves very significant performance gain compared with previous state of art. Can you give us some more intuition about what are these significant gain comes from?
Basically, it might be because of the geometry that we have induced in the embedding layer. The embedding size, the training protocol has been basically used from the previous baseline, so we have kept the training protocol same. But the main intuition behind such improvement is the geometry that we have induced in the embedding layer.
Okay, thank you.
Thank you.
Thank you. And maybe a last question. For the paper number 2, the graph matching, will you consider in the future, beyond pairwise graphs, higher order graphs, or is it something?
Well, actually, the graph convolutional networks inherently models the higher order graph similarities.
Okay.
Okay, thank you. So, yeah, if we don't have further questions, next, thanks to the speakers again. Thank you.